China split a 2,700-kilometer desert in half and built an elevated railway above it all, 2,712 kilometers of it, which is roughly the same distance as driving from New York City to Las Vegas and back. You heard that right. Almost no one talks about what it actually took to pull this off. This is the story of how China engineered above one of the most hostile environments on Earth and why the desert nearly made it impossible. But before we get to the engineering, you need to understand what China was actually up against. The desert that swallows everything. The Taklamakan Desert doesn't forgive mistakes. You're standing at the edge of it now, and what you're looking at isn't the kind of desert you've seen in pictures. This isn't rolling golden dunes with a romantic sunset behind them. This is 270,000 square miles of shifting sand, extreme heat, and wind so violent it can bury a road overnight. The Chinese name for this place translates roughly to, "You go in, you don't come out." That name wasn't chosen lightly. Summer temperatures here regularly hit 122 degrees Fahrenheit at the surface. In winter, that same ground drops to -40. That's a swing of over 160 degrees Fahrenheit between seasons on the same patch of Earth, and the wind doesn't stop. Storm force gusts tear across the basin regularly, carrying walls of sand that can reduce visibility to 0 in minutes. But here's what makes the Taklamakan different from almost every other desert on Earth, and this is the part that should make you lean in. The ground itself cannot be trusted. Beneath the surface, ancient riverbeds and shifting sediment create a subsurface that behaves almost like a slow-moving liquid. Build something heavy on top of it, and over time it sinks, tilts, and eventually fails. And then there's the sand migration. The dunes here don't sit still. They move up to 328 feet per year, crawling across the landscape and swallowing everything in their path. Roads built through the Taklamakan don't last. They get buried. A railway built the same way laid directly on the ground would face the same fate. So China faced a choice with no easy answer. Fight the desert forever, or rethink the entire approach from the ground up literally. And that's exactly what they did. But the solution they landed on was more radical than anyone expected. The decision to go up. When China's engineers sat down to solve the Taklamakan problem, the answer they kept coming back to was the same one: stop trying to fight the ground and leave it behind entirely. The concept sounds simple. Build the railway on elevated viaducts, essentially one continuous bridge, so the track never touches the desert floor. The sand can shift beneath it. The dunes can migrate. The ground can heave and contract through its wild temperature cycles. None of it matters if the railway is floating above it all, on concrete pillars driven deep into stable bedrock, far below the surface chaos. But here's what you need to understand about the scale of that decision. This wasn't a short, elevated section through a tricky patch of terrain, the kind you might see carrying a highway over a floodplain. China was committing to building what would effectively become one of the longest elevated structures ever constructed by human hands. Thousands of concrete piers, thousands of prefabricated beam spans, stretching not for miles, but for the equivalent of crossing the entire continental United States from coast to coast, and then some. And they had done something like this before. China's high-speed rail network, already the largest on Earth, is full of elevated viaducts. The Danyang-Kunshan Grand Bridge alone, which carries high-speed rail between Shanghai and Nanjing, stretches over 100 miles and held the record for the world's longest bridge for years. China had built the playbook. Now they had to run the same play in conditions 1,000 times more punishing. Because a high-speed rail viaduct in the green lowlands of eastern China is one thing, a viaduct in the Taklamakan is something else entirely. The wind loads here are in a different category. The temperature extremes are brutal. The remoteness means there is no nearby infrastructure, no ready supply chain, no margin for error. Every design decision that worked in gentler terrain had to be stress-tested against conditions that push materials and engineering to their absolute limits. But the biggest problem wasn't the wind, or the heat, or even the sand. The biggest problem was what lay directly beneath the surface, and what happened when you tried to anchor something permanent into it. Anchoring into the abyss. Before a single beam could be lifted, before a single span could be placed, China had to solve the most fundamental problem of all. How do you anchor something permanent into ground that refuses to stay still? The answer starts deep, much deeper than you'd expect. Standard railway foundations sit relatively close to the surface. In stable ground, that's fine. But in the Taklamakan, the unstable sediment layer doesn't end after a few feet. In places, it runs down nearly 100 feet before you hit anything solid enough to build on. So China's engineers designed pile foundations, massive concrete columns drilled vertically into the earth beneath each pier, some of them reaching depths of over 100 feet, to lock into stable geological substrate far below the shifting surface chaos above. Think about what that means in practice. For every single pier along this railway, and there are thousands of them, a crew had to drill down through 100 feet of unreliable desert ground, pour a concrete column into that shaft, and then build upward from there. Multiply that by the full length of the line, and you begin to understand why this project demanded a construction effort unlike almost anything attempted before it. But the foundations were only half the battle. Once the piers were up, the spans connecting them had to survive something that foundation engineering alone couldn't fix: the wind. Desert storm force winds in the Taklamakan regularly exceed speeds that would shut down construction on a normal job site. Here, they're just another Tuesday. And wind hitting a long elevated structure doesn't just push it, it creates complex lateral forces, vibration, and uplift pressure that can work against fasteners, connections, and joints over thousands of cycles until something eventually gives. So the pier designs weren't just tall concrete columns. They were aerodynamically shaped, their cross-sections engineered to split the wind and reduce lateral pressure rather than taking the full force of a gust head-on. And then there was the heat. Concrete expands in heat and contracts in cold. Steel does the same. On a structure exposed to a temperature swing of over 160 degrees Fahrenheit across the same year, those expansion and contraction cycles are enormous. Every rail joint, every beam connection, every fastener along 2,700 kilometers of elevated track had to be engineered to absorb that movement without cracking, loosening, or failing. The concrete mix itself was redesigned, adjusted to cure properly in extreme desert heat, where standard mixes can dry too fast and develop internal fractures before they ever carry a single load. Here's the part that most people never consider. The railway isn't a static structure sitting quietly in the desert. It's a living, breathing system that expands and contracts every single day, and every single component was designed to handle that movement for decades, without maintenance crews being able to reach most of it easily. But even with perfect foundations and perfectly engineered spans, there was still one enemy that no amount of concrete could fully stop. And it was coming from every direction. The sand fights back. You'd think that once the railway was elevated, lifted clean above the desert floor, the sand would stop being a problem. That's what makes this next part so brutal. The sand doesn't need to reach the track to cause damage. It just needs to reach the base of the piers. Wind-driven sand is essentially a slow-motion sandblaster. At ground level, it hits the concrete piers thousands of times a day, every day, year after year, gradually eroding the surface, working into micro-cracks, and over decades, compromising the structural integrity of foundations that the entire railway depends on. And if the dunes themselves migrate close enough to pile against the pier bases, the lateral pressure alone becomes an engineering threat. China hadn't just built a railway above the desert. It had planted thousands of concrete pillars directly into it, and the desert was going to spend the next 100 years trying to tear them back out. So, alongside the railway itself, China deployed what is essentially a parallel defense system, and it's one of the most ingenious low-tech solutions you'll find anywhere in modern infrastructure. It starts with sand fences, long barrier walls installed on the windward side of the track corridor, designed to reduce wind velocity at ground level before it ever reaches the piers. Slow the wind down enough, and it drops the sand it's carrying before it gets close. Simple in concept, extraordinarily effective in practice when deployed at scale across hundreds of miles of open desert. But the fences alone weren't enough. Directly around the pier bases, crews laid what's known as a checkerboard grid, an ancient Chinese sand stabilization technique scaled up to an industrial level. straw, and gravel, packed into a grid of 1 meter squares, each cell acting as a trap that catches wind-blown sand, breaks the surface wind flow, and prevents the ground from deflating away from the foundations. It looks almost primitive next to the engineering above it. But it works, and it had been proven across decades of desert reclamation projects in China before it was ever applied here. Then came the chemistry. Polymer-based binding agents were sprayed directly onto exposed sand surfaces around the foundations, essentially gluing the top layer of the desert into a temporary crust, hard enough to resist wind erosion. Not permanent, not intended to be, but enough to buy time for the biological solution to take hold, because the final layer of China's sand defense wasn't concrete or chemistry, it was alive. Drought-resistant plants, saxaul trees, tamarisk shrubs, native desert grasses were planted in stabilized zones along the entire corridor. Their root systems bind the sand permanently. Their canopies break wind velocity at ground level, and over time they transform the managed strip alongside the railway from bare desert into a thin but functional biological barrier. And here's what you need to understand about all of this. It never stops. The sand fences need inspection. The checkerboard grids need repair after major storms. The vegetation needs monitoring. The chemical crusts degrade and need reapplication. China didn't build this railway and walk away. It committed to a permanent, ongoing negotiation with one of the most aggressive natural environments on Earth, and losing that negotiation, even briefly, has consequences measured in millions of dollars and structural damage that's almost impossible to repair remotely. But managing the sand around the railway was only possible because crews could actually reach it. And getting crews and materials to the middle of the Taklamakan in the first place was a problem that almost stopped this project before it ever began. Building at the edge of the world. Here's something that doesn't get talked about enough. Before China could build this railway, it had to build the ability to build it. The Taklamakan has no interior road network, no supply depots, no construction infrastructure of any kind. The towns that dot its perimeter are connected by roads that hug the desert's edge, but push inward toward the heart of the basin, and you're on your own. No power lines, no water sources, no shelter. Just 270,000 square miles of hostile, indifferent desert that has no interest in making your construction project easier. And this was just the beginning of the problem. Because before a single pier could be drilled, before a single beam could be lifted, China had to answer a question that had no clean solution. How do you move hundreds of thousands of tons of steel, concrete, and heavy machinery into a place that doesn't want you there and has no roads, no water, and no margin for error to offer you? The answer was brutal in its simplicity. You build the infrastructure of construction before you build the railway itself. Temporary access roads were carved directly into the desert rough, packed sand tracks, capable of carrying the kind of heavy vehicles that would make this project possible. Not paved, not permanent. Just functional enough to hold together long enough to get the job done, but without them nothing else moved. Then came the concrete problem, and this is where it gets staggering. You cannot transport wet concrete across desert distances. It sets before it arrives. So China established mobile batching plants at intervals along the entire route, each one manufacturing fresh concrete on-site from raw materials trucked in from hundreds of miles away. And water, the thing you need to make concrete, to suppress construction dust, to keep thousands of workers alive in 110-degree heat, had to be planned for, piped in, and accounted for down to the last liter. In a desert with almost no natural water sources, water itself became a construction material. But here's what most people never picture when they think about a project like this. All of it. The roads, the batching plants, the beam yards, the water logistics, the worker camps was running simultaneously across hundreds of miles of active construction front. China didn't build this railway from one end to the other. It attacked it from dozens of directions at once, running parallel construction teams across the entire corridor at the same time, each one dependent on a supply chain that was being held together by sheer organizational force in one of the most punishing environments on Earth. Workers operated in temperatures exceeding 110 degrees Fahrenheit. Shifts were cut short during peak heat. Equipment broke down faster than it would anywhere else, and when it did, there was no backup supplier an hour away. No parts store down the road. Every delay cost more. Every mistake took longer to fix. Every single problem that would be a minor inconvenience on a normal job site became a serious logistical crisis in the Taklamakan. And yet they finished it in roughly 3 years. That number should stop you cold. 3 years to drill thousands of foundations into unstable desert ground, lift thousands of prefabricated beam spans into position, deploy hundreds of miles of sand control infrastructure, and connect it all into a functioning railway in one of the most inaccessible places on the planet. But once you understand why China needed this railway badly enough to endure all of that, the 3 years stops feeling impressive and starts feeling inevitable. Because the prize waiting on the other side of this desert was enormous. Why the desert had to be crossed. Nothing about this railway was accidental. Every drilled foundation, every elevated span, every sand barrier and biological corridor, all of it existed in service of something far larger than an engineering achievement. And to understand what that something was, you need to understand what's been sitting underneath the Taklamakan and around it for centuries, completely out of reach. Xinjiang is China's largest administrative region. It covers over 640,000 square miles, nearly a fifth of the entire country's land area. And beneath its surface sits one of the most significant concentrations of natural resources in Asia: oil, natural gas, coal, rare earth minerals. The kind of reserves that don't just power economies, they determine which countries hold leverage over others for generations. For decades, those resources sat stranded, not because they couldn't be extracted, but because getting them out reliably, at scale, cost-effectively, was nearly impossible. The roads were vulnerable to the same desert conditions that buried everything else. The existing rail connections were limited, indirect, and nowhere near sufficient for the volumes China needed to move. The resources were there, the access wasn't, and that gap was costing China enormously. But then came the part that made this railway not just economically valuable, but strategically essential. And this is the piece that most coverage completely misses. China's coastal supply chains, the ports, the shipping lanes, the eastern infrastructure that powers the majority of the country's economy are exposed. They run through contested waters. They pass through choke points that foreign navies can threaten. For China's long-term strategic planners, depending on those routes for energy security isn't a risk, it's a vulnerability. An inland corridor that moves resources from Xinjiang to the rest of China entirely overland, entirely within Chinese territory, entirely independent of any foreign bottleneck that changes the equation in ways that go far beyond economics. And then there's what the railway does for the people living along its path, and this is the part that hits hardest when you actually think about it. The oasis towns ringing the Taklamakan have existed for thousands of years in near total isolation from each other. Connected only by dangerous desert roads, separated by terrain that punished every attempt to cross it, these communities watched the rest of China modernize around them while they remained cut off. Agricultural products rotted before they reached a market far enough away to buy them. Raw materials sat unmoved because trucking costs made extraction uneconomical. Entire regional economies were frozen in place not by lack of effort, but by lack of connection. The Hotan Ruoqiang Railway didn't just give those towns a train. It gave them access to everything that access unlocks: markets, investment, supply chains, opportunity. For the first time in their history, every oasis settlement around the Taklamakan's perimeter sits on a continuous loop of rail, connecting them to each other and to the rest of the country. The desert that spent thousands of years keeping them apart has been lifted over, and what's left on the other side is connection. China didn't build this railway because it was easy, or cheap, or convenient. It built it because the alternative, leaving that much resource, that much territory, and that many people permanently on the wrong side of the desert, was a cost it decided it was no longer willing to pay. And now you have everything you need to understand what this railway actually is. Above the desert. Come back to where you started. You're standing at the edge of the Taklamakan, and stretching out in front of you, disappearing into the heat haze on the horizon, is a concrete spine rising clean out of the sand. Pier after pier after pier, each one drilled deep into stable ground far below the surface chaos. each one carrying a continuous ribbon of elevated track that the desert has been trying and failing to reclaim since the day it was built. This is what 2,712 kilometers of defiance looks like. The dunes still move beneath it. The wind still tears across the basin at storm force. The temperature still swings over 160 degrees Fahrenheit between seasons. None of that has changed. The desert is exactly as hostile as it has always been. But running above it, on schedule, in any weather, year-round, are trains, carrying coal and oil and freight, and people across terrain that once made all of those things nearly impossible. China didn't tame the Taklamakan. You don't tame a desert like this. What China did was more precise than that and more permanent. It identified every single way the desert could destroy a railway, engineered a specific answer to each one, and then executed that plan across a distance that would break most construction programs before they reached the halfway point. Unstable ground solved with foundations drilled 100 feet deep. Sand migration answered with barriers, grids, chemistry, and biology working in layers. Extreme heat and wind absorbed by aerodynamic piers, redesigned concrete, and expansion joints calculated to the millimeter. Total remoteness overcome by industrializing the construction process itself, building the supply chain before building the railway. Every problem had an answer. Every answer was engineered. And when you add it all up, what you're left with isn't just a railway. You're left with proof that geography is no longer a permanent barrier, only an engineering problem waiting for someone ambitious enough to solve it. China looked at 270,000 square miles of desert that had stopped civilizations for thousands of years and decided the answer wasn't to go around it, it was to go above it.